All right, so let's just carry on. So I introduced the book of Gabriele Eichwedler in my last lecture, but she has written some other articles, some other books as well. I also introduced Christian Temmer. She is a German mathematician, and she's interested in location theory and multi-objective optimization theory in general. And so the problem of multi-objective optimization could be written as this one. So f is a vector vector, and so we have m different objective functions, and the g of x is inside a cone, a convex cone, and the constraint is of, so when we say omega, it is our decision space, and f of omega is our objective space. So we will discuss only minimization problems because any maximization can be transferred to a minimization by just multiplying a negative minus 1. So we said that dominated points are points that are, so we are trying to make some order on the structure of all points, so that the green points are the points of efficient frontier that we are interested. And so you understand why we need the concept of order and domination. Of course, it has its roots in functional analysis and in Banach spaces in general, but you'll notice that this is a very interesting concept and approach to multi-objective optimization in general. So we can define an order in different ways. One of them, you could specify your preferences by domination or partial ordering. And the inner product space, Hilbert space, covers many spaces, such as the linear algebra that we always do in engineering is just a very small, space. But you can go to Banach spaces, locally convex, and more generally, the most general space is the vector space. So we understand all of them are just topological spaces, and and ordering is just one of ways we can define our topology, or the space that, for example, in optimization, the space of decision space and the objective space that we want to talk about is finite dimensional, but function spaces in general, function space theory, is an infinite dimensional. For example, Sobolev space is an infinite dimensional. So our problem in multi-objective optimization, when we have just infinite multi-objective functions, is so easy. So partially ordered it is useful in many contexts. For example, in Zorn lemma, if we know that the upper bounds, for example, of a chain, then it is necessary. For example, you can understand what is the least maximal element of that. And partial ordering by convex cones is a very important topic in modern optimization, because, as I said, we try to define in what order. To define an order, to understand, to make a topology on the decision points that we want to understand. In which direction should we go to get closer to the efficient frontier? So you'll see why is it so important. So a subset of a vector space is called the cone. If for all real R, so RC is inside that cone. So it is pointed if it just includes the origin. And a cone is convex if this relation holds. And the intersection of any non-empty family of cones is again a cone. So useful property. So we defined partial ordered linear space as, for example, a pair. It's like a pair. All the pairs that you can define an order on that. For example, if you have a cone, you can just use this property to define that cone. For example, x is less than y in k is your cone, if y and x, y minus x, belongs to that cone. So we can make some orderings. We can define partial orderings on your points, so that we understand in which direction should we move. For example, we move in this direction, so that to get closer to the efficient frontier. And it is useful. So you see, in two-dimensional and three-dimensional, you can understand it, you can observe it. But in higher dimensional, this is all the abstractions that helps you. So the minimal solution of objective optimization. So when we say a point X in decision space is a minimal solution with respect to the ordering of cone K, if f of x bar is a K minimal point, the set of all of them is called M. And so the image of that, we call it efficient set. This is the efficient set. So we go from the decision space to objective space. I'm just reviewing. And so if there is a point, then we say that f of x is dominated by f of x bar. And corresponding, and also in the decision space x, we say x is dominated by x bar. And if it is a special cone, then we say it is EP minimal point. So we can talk about that in later. That is the reason why, in general, non-discrete multi-objective optimization problems have an infinite set of... Because, for example, in R2, if it is 2, 1, and this is 1, 2, okay? So we cannot compare these 2 points, as I said. And so we can also define lexicographical ordering, and we can define total order, but so let's come back to our original problem. We said that all of the optimization, multi-objective optimization, most of them, such as weighted average or epsilon constraint multi-objective optimization, are just a special case of Pascoletti-Serafini Scalarization. So it's interesting that we just minimize t, and because it's just a scalar, so we just reduce t until it is the least, until it is the minimum of all t. And of course, it should satisfy these feasibility conditions. So when we want to solve MOP, multi-objective optimization, so this one is just trying to use weak assumptions, weak solutions to cover all strong solutions. So it's typical things that we do in mathematics. So as I said, scalarization problem is a kind of is a weak approximation of multi-objective optimization, and so this is our problem. But we try to go and cover the space by some, I will say, some hyperplanes, and so we just need to know the reference point A, and in which direction should we move to search the space. So that's why A plus TR covers this line. And R and A, those are inside RM. So we go in a special direction. And so this is another formulation. We can go out and but why y bar is k minimal if this if this holds. And the geometric intuition, as I said in my previous lecture, is like this. So we go in the direction of R, and we start, for example, in many articles, they say they have written multi-start. It means that you initialize your algorithm with many different solutions. And so, for example, our reference here, A could be here, A could be here, but the direction is here. Direction is R. And in future, I will show you how to relate R to some parameters when you want to define the polyhedral cones. And so you have only A. So in this book, you have only A and R as your parameters to make to find the efficient points. But in some other journals or books, you see they even change the cone. For example, this cone is inside another cone, and it's just a chain. And that's very general. It's so interesting for mathematicians as well. But here in this book, we fix K. We say that, okay, our polyhedral cone is fixed, and we just want to change two parameters. And A plus TR, and so we have only A and R to change to go to get closer to the efficient frontier. And so there is an efficient frontier here that the image of some points that are, for example, W stands for weak. So we have weak, and if we don't mention that, then it is not weak. So we consider the scalar optimization problem, and I want to prove first one. For example, I want to prove that if interior of K of your cone is not empty and is not empty, then if X bar is a weakly K-minimal solution of multi-objective optimization, then 0 is a minimal solution of SP. For if we just choose A. So when we say X bar is a weakly K-minimal point, and interior of K, of course, is not null, then f of x bar, according to definition, f of x bar minus interior of K is inside f of omega. And from this, I want to prove that if we just set A is equal to f of x bar, then not only f0 and x bar is a physical point, but it is a minimal solution of SP A and R. So it is a minimal solution of that. So I want to prove it by contradiction. So I just assume that there exists a point T prime and X prime. T prime is less than 1 because we want to do, that is the optimal point. We have found another point. I want to prove it by a contradiction. So I've assumed that it is not a minimal solution. So there exists T prime and X prime such that T prime is less than 1 and K prime, of course, is inside your cone. And it satisfies the feasibility condition A plus minus f of x prime is equal to K prime. And if we know that we substitute A by f of x bar, so we will see that f of x bar is equal to f of x prime plus K prime minus T prime R. But because both R and K prime is inside K, so we say this is inside interior of K. And then we understand that f of x bar is inside f of x prime plus interior of k. And this is a contradiction because we assume that x bar is weakly k minimal. So it's a contradiction. And so we have proved the part A of this theorem. And